We're going to finish up our section on graphs of functions by talking about even and odd functions which have special symmetry on the graph. So an even function, by definition, is where for every x, f of negative x is equal to f of x. Okay, that's the algebraic definition. When you plug in, say, 2 and negative 2, you get the same y value. 4 and negative 4, you get the same y value. It gets its name from even power functions. If you take x squared, if you take negative x and x and you square it, you get the same result. Okay? So for any even power, you're going to get an even function if you look at x to the n for an even power. So the graph of those, if you think about what they look like, they're symmetric about the y-axis. If you go out the same distance to the left and the right of the y-axis, you're going to get the same y values and you get symmetry. Okay? Think about y equals x squared. Look at that graph and you'll see a good example of what we mean. We can show that a graph is even using the definition. So if we want to show f of x equals x squared plus 5 is even, then what I need to do is show that if I plug in negative x, I get the same thing as if I plug in positive x. My formula doesn't change when I plug in negatives. Even powers and absolute values cancel negative signs, so they're even. When you combine things together, though, you have to be careful. The plus 5 doesn't affect it. You can actually think of it as being 5x to the 0, since x to the 0 is 1, and 0 is even. If all your powers are even, it will be even. If they're mixed up, it'll be neither, and if they're all odd, it'll be odd, if you're talking about polynomials. But anyway, in this case, if you plug in negative x squared is x squared. Okay? It would cancel the negative, and you get x squared plus 5. So f of negative x, the formula is the same as f of x. So that shows that it's even. I forgot to make that it said to make the graph when I did the PowerPoint here. I'll just graph it for you on the calculator. So we got y equals, clear it out, x squared, which is a nice parabola, plus 5, shifted up 5. You see that it has the vertex at 0, 5, and it's symmetric across the y-axis. If I were to be able to fold this thing on the y-axis, the two pieces would land on top of each other. Okay? Part B is completely unconnected to Part A, except they're both talking about even functions. This is not the graph of x squared plus 5, obviously, in the picture. But it says complete the graph shown, assuming the function is even. Okay? If I was drawing this by hand, what I would do is pick the important points and then look at their reflections. Okay? Where the idea is it's even. We're going to get the mirror image over here for the other half. So, of course, 0, 6, that's on the axis. If I reflect it, I still get 0, 6. We have an x-intercept at positive 6, so we should have an x-intercept over here at negative 6. So we could draw that point. And it looks like it's at about 7, negative 1, so we'd have negative 7, negative 1. And then that point that's at 8, 0, we'd have negative 8, 0. And then 10, not quite 1, 10 and about 0.75 or so, we'd have negative 10 and about 0.75 or so. I was able to take my computer and just copy the red part and flip it to see that picture there, but that's what it would look like. Again, if you were trying to draw it by hand, just pick out some of those key points, like the 6 will go to negative 6, the 8 to negative 8, and you have that shape for the even function. Okay, let's do the same thing for odd. Talk about odd. By definition, an odd function, if I plug in x and negative x, I get the opposite sign. We say f of negative x is equal to negative f of x. That's saying if I do like 2 and negative 2, I'm going to get opposite signs. And the name comes from odd power functions. If you take x to the third and you plug in, say, 2 and negative 2, you're going to get 8 and negative 8. Same number but opposite sign. These wind up being what we call symmetric about the origin. That's a 180-degree rotation or a reflection across the x and the y-axis. They call it symmetric about the origin because the origin stays fixed if you were to reflect something that way or rotate that way. It's a 180-degree rotation about the origin. So if you want to show something's odd, you have to show that when you plug in negative x, you get negative f of x, or in other words, all signs change. And all odd powers are going to do that. So if you look at f of negative x in this case, for x to the third plus x, we've got negative x to the third plus negative x. Well, the negative would not cancel the negative, or the odd power would not cancel the negative sign, and I would get negative x to the third minus x, or you can factor the negative out. We have negative x to the third plus x. So all the signs change. We get the opposite sign, so that's negative f of x. The graph, what you would do is change both signs if you pick a point. So 0, 0 is not particularly helpful. Again, it's going to be about the origin. So But we have a point here, let's see, 2, -6. It'll go to -2, +6. I'm going to go ahead and fill in the picture here. So that point, the min here goes to this max. 2, -6 goes to -2, 6. The point that's at, let's say, 5, 0 will go to -5, and of course -0 is still 0. 10, 10 will go to -10, -10. So if you take a point over here on this side of an odd function, change both signs, you'll get a point on the other side of the odd function. And they get this, we call it a symmetry about the origin. If I were to reflect this first across the x-axis and then reflect that across the y-axis, it would land on top of it. Or if I were to rotate this entire picture 180 degrees about the origin, it would land right on top of where it was originally.